Deep inside the volcanic fissures of Hawaii, geologists recently uncovered a chemical anomaly. Embedded within the freshly erupted lava, researchers found unexpected traces of gold and ruthenium, elements that typically reside thousands of miles below the surface. For decades, the standard model of geology held that Earth's core was effectively isolated from the crust. The assumption was that the core mantle boundary was a hard limit, keeping the center of the planet chemically separated from the world above. But specific isotope signatures in the Hawaiian lava show this boundary is porous. The data indicates that hundreds of quadrillions of tons of superheated rock are rising on deep mantle plumes, transferring material from the core to the crust over millions of years. Finding these precious metals in a deep mantle leak presents a paradox. To understand how these incredibly dense elements became concentrated at the center of the Earth 4.5 billion years ago, we have to look at how they are manufactured in the cosmos. Stars act as the universe's element factories. Through stellar nucleosynthesis, the immense gravity inside a star's core crushes light atoms like hydrogen and helium together, fusing them into heavier elements and releasing the energy that keeps the star burning. This chart plots fusion energy across the periodic table. It climbs efficiently for lighter elements, but hits a hard vertical boundary at iron 56. Past this, fusing heavier atoms absorbs energy. The engine stalls. Standard stars physically cannot manufacture heavy precious metals like gold or platinum. Since normal stars cannot forge elements heavier than iron, the gold leaking from Earth's core requires a manufacturing mechanism far more violent than a burning star. To forge the heaviest elements in the periodic table, the universe relies on a specific environmental loophole, a cataclysmic flood of free, unattached neutrons. Physicists call this the R process. Neutrons bombard a seed nucleus faster than it can decay, making it balloon into a heavy element. Researchers assumed standard supernovae provided this neutron density, but models proved they don't reach the extremes required to explain the universe's gold. To manufacture the volume of gold and heavy metals trapped inside our planet, the universe required an impact of unimaginable density that humanity had never observed in real time. That changed in August 2017. Deep space observatories picked up a sudden gravitational wave alert, directing astronomers globally to the site of a massive cosmic collision. They witnessed a kilonova. Two hyperdense neutron stars, caught in a decaying orbit, violently spiraled into each other until colliding in a blinding shockwave. By analyzing the light spectrum from the expanding debris cloud, researchers found the unmistakable chemical signature of freshly forged heavy elements like strontium, bred directly in the chaos of the collision. This single collision provided the direct evidence needed to map the R process. It confirmed that the universe manufactures precious metals during the final moments of a neutron-star merger. Once forged, these heavy atoms cool and drift across the void. Over millions of years, this metallic dust seeds the primordial gas clouds that eventually collapse to form new star systems. About 4.5 billion years ago, a portion of this debris coalesced to form the early Earth. Because these heavy elements possess extreme density, they immediately sank through the molten layers of the young planet, pooling at the center. They remained trapped at the core mantle boundary for billions of years. Now, slow, steady streams of superheated rock are sweeping up microscopic traces of those heavy metals and carrying them back toward the surface. The gold and ruthenium found in the Hawaiian mantle are not native to our world. They are the radioactive debris of a dead star collision that occurred before our solar system existed. Every ounce of precious metal used in human civilization, from global currency reserves to the circuitry in our electronics, shares this identical origin. This forces a shift in how we view the planet's interior. The core is no longer just a molten engine. It is a preserved reservoir of the ancient universe. By isolating the microscopic metallic traces cooling in these volcanic craters, researchers are reading a physical record of events that happened light years away and billions of years ago. The deepest, most inaccessible parts of our world are finally becoming legible. To understand the history of the stars, we simply have to look beneath our feet.